Sometimes you can draw more than one good Lewis structure for a molecule. So consider the NO2- ion. Nitrogen provides 5 valence shell electrons, oxygens each provide 6, and the negative charge provides 1. And now we can draw a Lewis structure. This is a perfectly good Lewis structure. All of the atoms have a satisfied octet. The formal charges are all minimized, and everything seems to work out quite well. However, we could also draw this Lewis structure. This Lewis structure also has satisfied octets and appropriate minimized formal charges, and there's no way to decide which one of these two structures is better. They're effectively the same. And when you can draw more than one equally good representations, they're known as resonance structures. And you write them separated with a double-headed arrow, like this. And this implies that the structure on the left and the structure on the right are in resonance with one another. So in practice, it's not like NO2- is switching back and forth between those two structures. It's more that NO2- exists as a sort of average between those structures. So if you look at the bonds in NO2-, one of them is a double bond and one of them is a single bond for both of the resonance structures. But in practice, it's more like both of the bonds are kind of 1.5 bonds. And you've got something like this. The bonds are somewhere in between a single bond and a double bond, and that includes things like bond length and bond strength. An important point is that in resonance structures, the atoms all stay in the same place. It's really only the electron positions that can change. You're drawing different Lewis structures for the same molecule, not an isomer of that molecule or anything like that. And another common example you might come across is benzene. These two Lewis structures are effectively equivalent. There's no way to decide which one is better. All the atoms are in the same positions. It's only the positions of the double bonds, so the electrons, that have changed. And experiments have shown that in reality, benzene doesn't look like either of these. It looks like an average of the two. And in real life, all of those carbon-carbon bonds are identical. And another way that we can represent something like this, where you have a ring structure that has a series of alternating double bonds, is like this. And you draw a ring in the center, indicating that there's resonance structures that make up this molecule. And there are a number of benzene-based molecules, and they all behave kind of similarly to this. You can also draw more complicated resonance structures, like this one. The left-hand example is electrically neutral. All the formal charges are 0. And the version on the right-hand side is also electrically neutral, but all the formal charges are not 0. So this is what's known as a zwitterion, where it's got a positive and negative charge that cancel out to make a neutral structure. The example on the right-hand side is not quite as good a Lewis structure, according to the general rules that we follow, as the one on the left-hand side is, but it's a Lewis structure that can be drawn that has relatively low formal charges, that has full octets, and has all the atoms in the same place. The only thing that's different is the position of the electrons. So these two are still resonance structures. And this kind of strange structure is going to be much more common when you get to organic chemistry.